Hi guys, I'm Animesh, this is my YouTube channel, and today we are going to be solving the INOI problem brackets. Now this problem appeared in the Indian National Olympiad of Informatics in the year 2016 and is one of the least solved problems on CodeChef with just under 100 successful submissions currently. So today we are going to be taking a look at how to approach such a problem and how to go about finding a good solution to such a problem. So let's just dive straight in.
If you want to read the problem statement for yourself, please follow the link in the description below. However, in a gist, the question states that there are k different types of brackets, each with an opening bracket identified by a number from 1 to k and a closing bracket identified by a number from k plus 1 to 2k. Now we are given the sequence of brackets and their values as an input, and we are asked to find the subsequence of brackets which is well bracketed and has the maximum sum of values, where a subsequence is any array which has the same sequence of elements as in the original array but may or may not include any of its elements. So you are free to drop as many elements as you want. Also, well bracketed implies that every opening bracket has a corresponding closing bracket that comes after it, and no two pairs of brackets are entangled between each other. So now that we understand the problem, let's get working on the solution. The first step in solving any of these problems is to find out a brute force solution to it. Here, we must try all of the 2 to the power n subsequences and check them if they are well bracketed, and then find out the maximum sum from amongst them. Since there are 2 to the power n subsequences, and it will take quadratic time to naively check them, we are going to end up with a 2 to the power n times n square running time, which is way too big for solving any significantly large problems, but will get us partial credit for the test case with n less than equal to 10. Now that we understand the problem and a way to brute force it out, let's decide upon an algorithm to solve this problem well. We'd always start by thinking of standard algorithms to solve any problem, and here dynamic programming fits the bill. Other algorithms like greedy or graph theory, etc., should always come to your mind, but here they're easy to discard. Furthermore, this problem is very reminiscent of others like the minimization or maximization problems under certain constraints, or the longest palindromic subsequence problems, in which dynamic programming helps us lower the exponential time of the brute force down to a polynomial time solution. So dynamic programming seems to be the obvious choice. If you are unfamiliar with these problems that we discussed right now, please do follow the link in the description below. As soon as we see that we are going to be using dynamic programming, we start to think about how to break the problem down into subproblems. And here we try that if we know the solutions for a problem of size n, we try to find the solutions of size 1 greater. It is clear that the solution for a size of n plus 1 may be either the same as the solution for size n, or the bracket at the last position may get paired with any of the opening brackets in any of the previous positions. If a pairing is done, we know that the answer would be the sum of values of the two brackets plus the subsequence between these two brackets plus the subsequence before the first opening bracket. So now we know that we need to not only know the values of all of the subproblems starting from the first position of different sizes, but we also need to know the solutions of all of the subproblems of different lengths starting from all different positions. So to solve any problem of size n, we must know the answers of every single subproblem starting from every single position of all sizes from 1 to n minus 1. And that is what will help us to solve a problem of size n. So now let's take a look at what our dynamic programming matrix is going to look like, what subproblems we need to find answers to. Before we move on to actually writing the algorithm, let's see how each update will take place. Now here we have an array of size 8, where we have solved every single subproblem of length 6 or less, and now we are trying to find the answer to the subproblem that begins at position 1 and is of length 7. Initially, we know that our answer is at least as good as the answer of position 1 length 6, so we take that as our initial value. Now we start by beginning to pair the closing bracket at position 7 with each of the opening brackets at all prior positions. So the first one, position 1, pairs up with position 7, yielding us a best answer of 6 plus 28 plus 10, because 28 is our pre-computed best answer for the array from position 2 to position 6. Now we move on to the next bracket, which does not pair up well. Now we come to the next opening bracket, which yields us a best answer of 14, because that's the best answer from position 1 to position 2, plus 20, which is the value of the opening bracket at position 3, plus 0, which is the value of the best answer from position 4 to position 6, plus 10, which is the value of the closing bracket at position 7. And this will eventually become our best answer, as none of the other ones pair up well, and the maximum answer is 14 plus 20 plus 10, which is 44. And 44 will be the answer to our subproblem here. This will also be the answer to the full array, and you can check that yourself. And this is how we are going to perform updates. Finally, this is what our memorization matrix looks like. So let's do a sample run on the example provided in the problem statement. All subproblems of length 1 have best value 0 because there is no possible well-bracketed subsequence in length 1. Next, we move on to length 2, and we use the same technique as we did in the slide before to perform the updates. We notice that only the array starting at position 4, length 2, has any value because none of the other brackets pair up well. Now this value is 2 because it's the sum of the two brackets. Next, we move on to length 3, and few interesting things happen as the two curly braces get included in more and more subsequences, but no real updates take place. Finally, at length 5, we notice that the bracket at position number 2 gets paired up well with the closing bracket at position number 6, giving us a value of 13. This score remains the highest score at the array of length 6 starting at position 1, which will be our solution as it is the entire array. Now please do try to run this yourself and check the values for all of the subproblems. Now we are going to move on to writing a program. So here is a quick code walkthrough. First, we are going to start off by declaring two arrays, V and B, which will store the values in the brackets respectively. We are going to take the inputs, and then we are going to declare a memorization array, dp, of size n by n. Now let's set all of the elements of this array to 0 and move on to the crux of our algorithm. We are going to loop through all of the lengths less than n and all of the valid starting positions for each length, which is all the way from 0 to n minus the length. Now we are going to set the initial value of our answer for that particular subproblem to be the same as that of the subproblem of size 1 smaller and at the same starting position. Now let's check if the bracket that we have just encountered is a closing bracket, and if it is, we're going to loop through all of the positions before it and check which one it pairs up well with. Let's say that the bracket at position I matches the closing bracket at position pos plus len. The value of this pairing, which we are storing in the variable temp, will be the value at position I plus the value at position pos plus length, which is the values of the two brackets, plus the answer from starting position pos to ending position I minus 1, plus the answer from starting position I plus 1 to ending position pos plus length. Now you need to do the little bit of mathematics to convert these starting and ending positions into starting position and length, and make sure that there are no invalid memory accessions because you have a value less than 0 for your length. So that is why I've used the max functions here. Make sure of all of that, and if this line works well, your entire program is going to work well. Finally, we are going to be taking the maximum of the value we have currently computed and the existing value that we have solved for the subproblem. And that's it, we are done. We'll be outputting the value of the largest sized subproblem starting at length 1, and now we are done. That's the entire program. So finally, let's analyze the time complexity of this solution. So we have got n squared over 2 subproblems, and we are taking about n steps to solve for each single subproblem. So we end up with a total of almost n cubed steps and that's our asymptotic time complexity. Now you can see that the constant factor for this would be significantly low, because first of all we have half of that value. Each of the problems is of size n or smaller, and there are a lot of smaller problems, so that's going to take down the constant. And furthermore, not all of the brackets are closing brackets, so we are going to be searching for much fewer values actually. So it's a constant factor much less than 1, but the asymptotic time complexity is n cubed, and this actually manages to run in the given time limits.
And that's it, we're done. Now go ahead and solve this problem by yourself on CodeChef. Try to see if you understand every single part of the solution, and please make sure to like, share and subscribe to our YouTube channel. Leave your thoughts and suggestions in the comment section below, and we'll be uploading a lot more videos on physics and computer science problem solving, as well as some mathematics. We'll be uploading videos on more and more topics of study, so please keep watching, stay tuned, and until then, bye-bye.